Okay, hi everyone. I'm going to record this part of the lecture again because we didn't get through all of it in class. And there was a good bit of dead air, of course, since I gave people time to work on these problems in class. I also wanted to make it slightly clearer what I'm looking for on the exam, put some things in this review that are more relevant to the project. They're appropriate to bring up during a review of course material so far, but it may not have always been entirely clear, like the fact that I have lower standards to the exam because it's a timed thing. And, in a class like this, that 2 hour deadline effectively is a little bit artificial. You have to work on a deadline in real life, but you'll rarely be asked to turn something around in that period of time if you're working on statistical analysis in Stata or R or wherever. So it's just not very realistic. That's just a way that our course works, though, is that I do need to test you at some point beyond the paper, and this makes a little more sense than a take home in some respects. So anyways, I do have smaller expectations here than I do for the paper. And I also included some things that were kind of just FYI, things that you might find interesting, or things that I don't think were extraneous, in that I was showing you how you can solve some problems that might come up when you're trying to do simpler things using Stata. But since I don't expect you to ever master that in the confines of this course, because there are things that maybe took me a second to stop and think about how to do, I don't want you to worry too much about it for the exam. So with that said, I'm going to run through basically the answer key. You'll see here that I put up, and I might retitle this document to something more professional, but I chopped down the do file here. I'm going to post it as a separate thing. This will feel more like an answer key. I am going to leave some of the things in that are more pertinent to the final paper, but I've more clearly marked off the difference, and they're just in there in part so that you can get a sense of, like, again, what I'm looking for on the exam versus the paper, because some of the things I show in lecture are more germane to the paper. They're a little more advanced. So hopefully it actually helps to see the difference. I'm not going to do anything that we haven't done so far. I omitted things that were new. Again, it was probably good to show you that stuff, but I want to make this feel a little bit more like an answer key. So without further ado, let's go ahead and do this. Hopefully you're watching on 1.5 speed. I can already feel myself slowing down to choose my words carefully, as I tend to do when I record these things at home. Okay, so the first part of this, and I'll go through maybe the first half of the review pretty quickly, because I think that was a little easier. The first thing to do, is that we just need to load the data. On the exam, I will ask you to use some data that may or may not already be in your course folder. I actually can't remember if I put it in there or not yet, or you may have downloaded it, but at any rate, this part shouldn't be too difficult. We've been doing this a lot before. I did want to remind you, it's always good to give a periodic reminder that writing clear here does make it so that you aren't going to have errors when you rerun a do file, because as long as you always start with a clear data set, you're not going to get the error that the data in the memory have changed. But you should always remember that if you have not saved commands, well, clearing won't boot out the commands because they'll always appear in the window. But if you've made changes to the data, at a minimum, you should load those into a do file. If you haven't, pluck them out of the command history and pop them into a do file. Even though those are there for the time being, they'll go away once you close data. That's review, but I just wanted to remind you of that because it's can be such a pain in the butt if you happen to make a mistake with that. So let's load in this extract. And let's go ahead and give the data set a label describing its contents, as I mentioned. Sorry about that, had a little computer glitch. So we go ahead and label the data, and we can describe contents just to make sure that this appears correctly. We do see a label here. And now we're going to go ahead and relabel all of the variables in lowercase for convenience. This may or may not be more convenient for you depending on the way you typically code or the way you type, but for a lot of people, it's easier to not need to capitalize things, because otherwise Stata is can be written in lowercase for the most part. Most commands can be written lowercase. And in a lot of cases, the default is for variables to be lowercase. People tend to get used to lowercase variables. So here I'm doing that. And the asterisk just makes this apply to all variables. So it's a wildcard operator. We've talked about wildcards quite a bit. Mitchell's book mentions it in passing and maybe somewhat unsystematically. I've tried to make it more systematic when I've talked about it. But I won't make this certainly won't be a large part of the exam by any means. It might be a challenge question at the end or an extra credit question of some sort. So good thing to know about, but for the most part, it's a matter of convenience, and most of what we do isn't so complicated that it's strictly necessary. As you get a little bit more advanced, it can sometimes be the case that it'll effectively be necessary, but we don't need to worry about that too much. And when we talk about programming, we'll see that programming often offers an alternative to wildcards. Okay, so now let's talk about how many observations are in the data set. We actually got this from above, so there's no real trick here. One thing to note, though, is that observations don't necessarily correspond to the number of individuals in a data set, where individual means something like the number of distinct persons. Some people might use individual to mean like an individual observation, but that's kind of non-standard usage. If you're using individual in the colloquial sense to mean like a person, if you have, for instance, time series data, the number of observations and the number of people may not agree. Or if you have nested data, where you have like the number of countries and the number, maybe you have countries and provinces, and which of them are individuals. It's kind of hard to say, really. And if you have multiple provinces per country, then you're going to have, in that sense as well, you might have multiple observations per individual in the sense of country. So here we have this number of observations, 10,644. We can also have observations that don't correspond to the number of people because we have duplicates. And so now let's look at the number of duplicates here. So let's go ahead and use the commands that we've learned to check out duplicates. So we want to go ahead and flag them, make sure that the code actually identifies them correctly, which is more or less guaranteed, but it's good to just take a look at what you're doing before you drop anything. Drop the duplicates and then check out the results. So we can start by writing duplicates report ID. I often like to start by just going for the ID variable first, and we can, in this case, the data set is so small, it's pretty easy to just look and see what the ID variable is. And the reason to do that is that you might have some occasions where you just have a mistake in the sense of someone is given an ID variable that someone else was given, but otherwise they aren't duplicated. So let's start with this. And we see that there are some duplicates. There are 4 observations total that have a copy, so that means that there are 2 that are surplus or duplicated. Now let's see if they are outright duplicates or just ID duplicates. And we don't have any differences here when we don't restrict the variables to ID, and we don't in fact restrict the variables at all. So these are probably duplicates proper. Let's tag them. And someone in class asked a great question about this. Note that we don't need to be terribly careful when we write gen here as an option from this main command, because when you have gen as an option from another command, Stata is already programmed to generate it in a way that you should look up what it's doing in the help file for that command. Like you would want to check and see what does the generate option mean for duplicates. But generally speaking, you don't need to put as much work into defining the variable, because that when it's written as an option like this, you don't always have this option for one thing. And so if it is an option, that usually, in fact, I guess I would say always means that the command has been written with this option for the sake of generating a new variable in a very specific way. So we'll see that later on when we look at tabulate, which has an option to generate dummy variables from the possible values of all the variable you're tabulating. Stata, again, is programmed so that the generate option in that case just does that without needing further explication. So that's a really great question someone asked, and I just wanted to make that point clear. Okay, so we've tagged these. Now let's go ahead and list. So this just creates a dummy variable. We can actually tab is dupe just to see what this looks like. And we see this here. So this looks pretty similar to the duplicates report, except we don't have as much information because it's a simpler command. We just listed a dummy variable. So we don't have a ton of cases here. Cases and observations are synonymous. So we can just look at these individually and verify that they look pretty much exactly duplicated and they're sequential, which gives us some further confidence that they're true duplicates. So we can go ahead and drop them. You'll see that we dropped 2 observations. So Stata is smart and it will just go ahead and drop them like this. I'm actually not completely sure how it decides which of these to drop. In theory, it doesn't really make any difference. I suppose we could go ahead and list them again. And one thing to note here too, yeah, so it appears that it drops the latter instance. Makes sense. One thing to note here too is that we still have some variables or observations rather that are listed as having a 1 on the isDupe variable as noted in class, but that shouldn't make you worried because this isDupe variable is kind of a, it's not a very sophisticated variable. We just basically tagged people if they had a duplicate in the past, and that variable can't change without us directly changing it. It's not a command. So we just encoded information here, fixed information for the given observations. And so that won't change unless we do anything. We dropped a couple of people, but we didn't drop the other couple of people, right? So there's still going to be a couple of people who have this value because we only dropped the duplicates, we didn't drop everyone. So a way to verify this that will maybe be less confusing is to just run duplicates report again. And now if we do that, we see that this is a little more comforting. Although if you're paying close attention, you can kind of make sense of what's going on here, but it can be a little bit confusing at first. So I think it's a good idea to do this as well. All right, now we want to go ahead and use the code book that we have. I mentioned that I forgot to put this in the course data, so sorry about that. This part is pretty straightforward. Basically use Control F if the code book is large, put in the name of the variable. It's typically a skill that people who are kind of, I guess they say digital natives is the term, people who have grown up with PDF codebooks and things tend to, or not PDF codebooks, but PDFs, this tends to be second nature, so I won't belabor the point in the interest of keeping this short. And when in doubt, you can always use the table of contents too. So let's go ahead and just show what we could do if potentially more information were in the codebook in the data. On the exam, you may or may not have variables where this produces useful information. We've seen before in the GSS that oftentimes it's quite informative. Here it's not at all because these data have been deliberately treated by a past instructor, and I'm using the same data set for this first part of the review to be sort of cryptic for the sake of making you do a little bit of extra work. Work that's good for you because you're learning some stuff. So it turns out that this variable corresponds to country. So we'll rename this variable country. And then we wanted to go ahead and also label the variable. And so it makes sense to simply call it R as country. R is shorthand for respondent, of course. And then we want to go ahead and assign value labels. And I want to call attention to 2 things here. First, I'm going to put in the numbers that correspond to these country names, in part because when we have basically when the numbering system for a qualitative variable, and remember, a numbering system for a qualitative variable oftentimes isn't displayed, but it's still there in the background, right? These are just value labels. This actually is not a string variable, so there are still numbers that we're using here. So it's oftentimes not obvious what the numbers are, and if the numbers aren't just the first k natural numbers, where k is the number of possible values, sometimes that can lead to funny results. It's not especially relevant for us because not everyone is going to use multiple regression, but that's a case where you can get some really wacky results if you forget that these aren't numbered in this way. So it's a good idea to leave yourself a little reminder if you have this unusual situation. So far, we really haven't had that, and I show later on a way to basically eliminate this and reassign these to the first, how many do we have here? 1, 2, 3, 4, 5, 6, 7. So we could just assign these to the numbers 1 through 7. I show that later on, but it's not a bad idea to do it in the meantime. That was one thing I wanted to call your attention to. The other is that I'm using this shortcut here, this delimit shortcut. And basically what this does is temporarily tell Stata that the end of the line is not signified by just breaking a new line, which is formally referred to as carriage return. but it's actually going to be signified by a semicolon. And this command is one of a couple of commands that has to be run in conjunction with so you basically have like a setup command, which is this, and then you have a command that actually uses it, which is this, and they have to be run together. It might sound like a lot of work, but there's other things in Stata that work this way, including the important concept of a local, which is also an important concept in programming generally. So even if you don't do this kind of work in the future, but you keep doing something with computers, you find you have a passion for a little bit of programming or something like that, you'll encounter those constantly. So it's an important thing to know about. And that's another case where you have to run the kind of setup command and then the command itself. So it might seem like a lot of work. The reason I'm doing it here is so I don't have to keep typing the 3 forward slashes, which would be an alternative. So this kind of business here. Oops, that's too many here. And whether you choose one or the other, it's sort of aesthetic. If you have a really long line, especially if you're copying and pasting, so you don't have to actually type everything out, it can be a real shortcut to use this sometimes. Here, it's probably about an equal amount of work, but it's also something you might see if you look at other people's do files. And so I wanted to introduce you to it. So let's go ahead and assign the value label here. And this right here, hashtag delimit CR, just returns us to the carriage return, or the thing we've been using, where the end of a line, unless it's joined with the 3 forward slashes, just means the end of the command. And now we'll go ahead and label the values. Okay, so we've done this sort of process a number of times before, so hopefully it feels like review, but if not, that's how we do it. We define a value label, then we label the values of the variable with the value label. So now I wanted you all to create a dummy variable called mom worked that equals 1 if the respondent's mother worked when respondents were 14, 16 years old, and 0 if she did not. So give the variable a label and then check its creation. Okay, so how do we do this? First, let's describe the variable. And again, we can just use hand inspection here. If we had a lot of variables, as you may or may not in the exam, you can search in the variable window, or you can search using look for. So let's just show how we would do that here. Let's search for mother. And you might have to be a little bit flexible. Here we got lucky, but we could also try like look for mom. It doesn't bring anything up here. We could try look for work. So you can see it's not usually too hard to find what you're looking for. In some older data sets, you will need to consider the fact that they might have a lot of abbreviations. So if you don't find, like maybe I started by thinking about worked. I don't find anything for worked, but then I might just try shortening the word. Not excessively, you maybe don't want to search for W, but you might want to search for work instead. Or even WRK. I won't do anything too difficult in that respect on the exam, but that might happen to you in real life, and you may have to do a little bit of digging for variables on the exam. Okay, so we described the variable now, and we can get the value label here. Of course, there's oftentimes a pretty simple rule that maybe the value label is just the same as the variable name, or maybe in this case, because we made this lowercase, the value label is the uppercase version, and that's actually a common pattern as well. For example, on the most recent waves of the GSS. There are some cases where that's not true, and so just describing the variable is just a guaranteed way to get the value label. We can also check out the full distribution, and we see here, okay, so we've got basically one possible value that corresponds to what we want, and several that don't. We do have a numeric missing value here, which we'll need to be careful about, and then we have some proper missing values. Now we can go ahead and use that label list to look at the values just to confirm, because we already saw an example where this wasn't true, that these are ordered with the first k natural numbers. Here, that's true, although there's a gap, so we should be careful. On the other hand, we're going to reassign this to missing in a moment, so it's not a big deal. Otherwise, though, these look good. And you can see here we have this .n, but we don't appear to have anyone who is listed in that way. We don't appear to have anyone who is can't choose or not applicable. So it appears that we just have people who are system missing. So there's a variety of different ways to make a new variable here. I'm going to use truth syntax, which is pretty straightforward. It is something that I said at one point was kind of like more advanced material, but I've shown it every week since then. And it really isn't too different to what I showed you the first time I showed you how to make a new variable, where I showed maybe a couple more steps. initially I had us make an empty shell. So we wrote something like gen mom worked equals dot, and then we wrote replace mom worked equals, for instance, 1 if v58 equals 1. Here we're just telling Stata to be a more literal computer in the Boolean sense of operating with like really specific rules. So what we're doing here is saying generate mom worked equals v58 equals 1. This is kind of a funny thing, but what Stata is doing, just to refresh you, is deciding whether this statement is true. And so the benefit here is that it doesn't leave people for whom this is false missing. It leaves them as 0 because 0 can mean false in a certain way of, again, kind of like binary logic, basically, or binary arithmetic. So this is going to make a bunch of people who are 0 and a bunch of people who are 1. And then that leaves us with a little bit less to do because then we just need to handle missing values. So I can show you what this looks like right away. And you can see here, okay, we have on our new variable mom worked, it's a 1 if this is yes. And then as I mentioned in class, these are kind of censored here, but it's clear that they all mean no. So those are all zeros, that's good. But unfortunately, 9 missing and dot are also forms of that statement here, v58 equals 1. Those are also ways that that is false. So those are coded as 0. And we just want to make them equal to dot or system missing. Here in this case, we can just write replace mom worked equals dot if v58 is greater than 8, because remember that in some settings, this one included, Stata will understand this as a very, very large number. That's oftentimes tricky and inconvenient. Here it's actually useful because we can just say, okay, this was 9, we verified above that that also has the numeric value of 9. It's not just value label. So we can make these people and these people all in one go equal to 0. Missing, pardon me. We want to move them out of 0. So we'll do that now. And we'll check this again. And you can see that these people have all been moved here to system missing, which is good. Now we can make our value label. I won't go through this in detail because I showed this once before. And we'll make our variable label, but it's not a bad idea to just put this in the do file so that you remember that we should always do this, even though everyone might get even more bored than they might already be if I do that every time. So I'll spare you that. And we can check this one more time with the value labels, and this looks pretty good to me. So now we'll move on. So next, what I want to have us do is tabulate the social class variable v66, and I'm going to change this to reflect the fact that we made this lowercase. I decided to make it everything lowercase after we put these in here. So notice that a lot of people on this type of question tend to have a little bit of SDRB, or social desirability response bias, sometimes called social desirability bias. There's other names for it too. Basically, it means that people in surveys tend to answer, if they're not extremely strong-willed, they tend to answer what they think the surveyor might want to hear, or they're at least influenced in that way. So notice that very few people are reported being upper class. And so what we might want to do is try to assume that those people might have rounded themselves down to upper middle class. And then what we might want to do, for the sake of a lot of types of analyses, is, we've been doing this a lot, making dummy variables and thinking about basically, can we meaningfully split up this group of people into just 2 possible values? Because it is an ordinal variable, but we should still be really careful with ordinal variables, right? Because they're not actually quantitative, even though they're can be rank ordered. And so it's oftentimes a good strategy to start thinking about, how can I treat this? It's not, I don't want to say in binary terms, because that almost sounds like I'm suggesting you should try to think in a binary way. It's actually really sort of the opposite case, that a lot of times, especially as we go further, we're going to see that what we want to do is think about, how can I say something that is not binary and actually more complex in a way that uses only binary statements. And that's really how computers work in general. We're saying very complex things that aren't binary thoughts in the colloquial sense, only using a long set of binary statements. So that might sound kind of paradoxical, but it's, I guess it's not really paradoxical, but it's just a funny way to think about logic that is also kind of how computers work. Anyway, so it's oftentimes productive to think, can I somehow figure out a way to turn this into two possible values that are still meaningful? And so here it might make sense for some analyses to combine people who are middle class, lower class, working class, because those terms are self-chosen and they're not always well defined. We might think that that, generally speaking, reflects people who, say, work for a living in some sense, or are, habitually unemployed in the case of people who might call themselves lower class, but are in a similar general kind of class position to people who do work. And we might think again that some people in the upper class are probably rounding themselves down. Definitely in the US, right? There's almost like a meme about people saying upper middle class when they really mean extremely wealthy. People may be familiar with that phenomenon. So this makes sense. So let's try this. We're not going to do anything terribly different here. We're going to, again, get the value label. I'll try to skip through things I've already shown. We tabulate, check out the missing values, and we look at the label list, and we see that it looks like this. So we again have numeric missing, non-numeric or pseudo-numeric missing, and then we have some actual values. We can now use this new way of making a set of dummy variables. This is what I was referring to earlier. It's a case where we tabulate, and then we have this generate option, and Stata knows in this case to make a set of dummy variables that correspond to the possible values of V66. And you'll see that it does create a bit of an issue because, well, let's just run this up. Oh, shoot, I accidentally hit the entire do file, didn't select anything. If you ever do that and you want to stop a break, I think I mentioned this before, maybe not, but break is a good way to just stop it on its tracks. So now we can just rerun this from the start. And this is a nice thing about having the clear option here, is that I don't need to do a whole lot of work to just rerun every bit of code I've already written. I don't even need to go through and make sure that the data are cleared. Anyways, back to the main point here. So we generated a set of variables called class here, and we can go ahead and show how to describe these. Let's do that here. So we can just write d class like this, and this will describe all variables that start with class and then have character afterwards. So if we look here, we see we've got class 1 through class 7. This looks pretty good. You might be wondering, what are we going to do with this? Well, the cool thing is that these are all dummy variables, and they all have ones if this basically is the status of people on that variable. So since we plan to combine these two, we can just recode people who are ones on this to ones on this, or vice versa. And then everyone else is already a 0, which is what we want. We just need to be also a little bit cautious about this issue here. Okay, so let's go ahead and do the first part of that. We'll replace class 6 equal to upper class equal to 1 if class 5 is equal to 1. Again, noting to be careful about single and double equal sign, which is old hat for us at this point. Now, because this is the variable we want to stick with, let's rename it something catchy. Upper class seems like a good idea because that's who is a 1 on this. And we can make a value label. Here, this is a little bit cheating because we should have checked it first. And in this case, let's take a look at our missing values. And I don't know why I wrote already dealt. Oh, sorry, I wrote this because I was thinking that I was going to put in a little bit of extra work up here. This was not in the original do file. This is the thing I wrote when I was drafting this. So we did not actually already deal with missing values here, as you can see. In this case, we've got people who are missing, who are mistakenly reported as popular classes, which is just kind of a jargon for, not very scientific, but it's jargon for basically just, in the properly defined working class, and then people who might be considered petty bourgeois, which is oftentimes used as an epithet, but it's also a more specific term. Let's not get into the weeds of that, even though it is interesting sociology. Okay, so now we have the one variable that we really want, and we'll deal with the, I guess we actually need to deal with this here. So we'll show replace upper class equals dot if v66 equals dot, and we can do the same thing because that wasn't already a problem if this equals 9. And now we made some real changes here, and let's run this one more time to make sure we're good. And this looks like it's the way we want it. If you were one of these 4 lower classes, you were popular class on upper class. If you were upper class here, that means you were upper middle or upper class on the original variable. And if you were a 9 or system missing, you are now a dot here. So now we can go ahead and just drop those other class variables, and you can see they got a little smaller here in the variable window because we don't really need to use them. You can keep them around if you want, but they're easy to regenerate because we didn't change V66 at all. So yeah, it's really user's choice, but I don't think there's any reason to keep it. Now here, I put in a new question because I realized that even though this is a simple kind of question, and this is actually the main focus of your homework recently, so I didn't want to belabor the point because I wanted to show some things that weren't in the homework. I wanted to show it just briefly. So let's see if mom worked varies by the class variable. And let's use a numeric and a graphical method. So let's first use a numeric method. And I put less commentary here because I'm going to say this all out loud. I might add in some of this into the video file. So the numeric method, a two-way table would be fine. And you can see here that we have calculated row conditional probabilities because the predictor in this case is on the rows. You could argue that this in a certain way is also the predictor, right? Because this precedes this in time, assuming that someone's class status isn't really fixed until they're an adult, and this happened when they were a kid. But you could make a case either way. In this case, I've just stipulated that you should think about this as basically being conditioned on the class variable. So that's totally fine to do. You can always say, well, I think, do I want to use child's education to predict parents' education, right? You can do that it's not always clear why you'd want to do that. It's fine to say that if you're being careful and not saying causing, but predicting. But you should always just make sure you're doing what you think you're doing. So here, I am conditioning on the class variable, even though I could condition this other way. As a reminder, how do I tell which variable I'm conditioning on? Well, first of all, I wrote row here, but if I didn't write that and you were looking at this, what you would want to do is figure out which way do the percentages, which are the lower values here, which way do they sum to 100? So here they sum to 100, here they do not. So these give the marginal probabilities of mom did not work and mom worked right here. If we wanted these probabilities here, we would need to just calculate it the other way, unfortunately, although we could do that quickly. For instance, we can just copy this here. And if we look at it this way, now we can see the marginal distribution of class, and we can see this other way of looking at it here too. And somewhat predictably, based on the fact that inverse conditional probabilities always have to agree, and also just thinking about it sociologically, we see here that if your mom worked when you were a kid, you're more likely to be a member of the popular classes, so-called, and if your mom did not work, you were a little more likely in relative terms to be a member of the upper class. You're still more likely to be popular class overall. This is just a relative comparison, important point. And that corresponds with the fact that if you were a member of the popular classes, your mom worked relatively more when you were a kid. Okay. That's inverse conditional probabilities. See the supplemental lecture if you're interested in that. We could also add a chi-square test. I don't expect this on the exam. It's not a bad idea to do if you know how to do it, just because it's good to practice these things. The way we would do that, let me add a note here. Not required for the exam, but you may want to do this if you know how, and I would like you to try it for the project. I'll put that here. So we can add chi2. And here, it's clear what we're doing is doing a little bit of inference. And what this does, the chi-square test is kind of it's easier to understand exactly what it is when you're more familiar with a basic Z or T test. And hopefully people are, I know maybe not necessarily everybody is, it's technically a prerequisite, but it may have been a while since you took a course like that. Basically what this does is it tests the null hypothesis that these two variables are unrelated. what it reports here, this chi-squared statistic, basically represents how far out on the x-axis we are of a probability density function, or you can just think about it as a smooth histogram that represents the distribution of sample statistics if the null is true, or in other words, the sampling distribution under the null. It's easier to eyeball it when you have not a chi-square distribution, but a z or a t distribution, because then you can just think about it basically in terms of standard deviations. It's not exactly true for t when t is when your degrees of freedom are small, but close enough. Here, this is a little hard to visualize because chi-square distributions change pretty significantly when the degrees of freedom change, and also it's a little bit of a funnier shape. So just look at the p-value. Here it's reported as PR. PR in this context and P in that other context both refer to probability. This tells you the probability of results such as these if the null were true. So you have about a 0.1% chance of seeing results like this if the two variables are not related. That sounds like a kind of backwards way of saying things. I don't have time to explain that here. I have a bunch on that in my lectures for 360, which you'll have access to, or you can ask me about it. The reason for that is a little complicated. It actually has quite a bit to do with Bayes' theorem, if you're curious. And I can point you to some nice reading on that. In particular, a paper from Jacob Cohen, whose work we actually learned a little bit about in this past reading. That explains it pretty well, but I don't want to get into the weeds here. Just remember that a small p-value means that the null is unlikely. The null is virtually always a straw person, which you hope to knock down. Therefore, a small p-value actually, somewhat surprisingly, means that you basically have significant results. You could also do a proportion test too. This requires special conditions. It basically requires that the outcome be a dummy in Stata, or if you're doing it by hand, that doesn't have to be true, but you effectively have to convert it to a dummy. It just doesn't necessarily feel like you're doing that. And then you need to have your predictor be a dummy. That actually is the case here, so we can do that as well. So we're going to say PR test mom worked by upper class. And this gives results that are consistent with what we just saw. And in this case, you can see the p-value for a two-tailed test is 0.001. This output can be a little bit tricky to interpret because it's got some things here that are like this is basically a test of the difference going in one direction. So this is basically saying this test, the null against the alternative that the difference is greater than 0. And you can see here the subtraction that we're doing is the proportion of popular classes, the proportion of mom worked among popular classes minus the proportion of mom worked among upper classes. So this was positive in the sample. So we're going to have even stronger evidence for this one-sided test. This basically means we're looking at only one tail of the sampling distribution in the area underneath it. A lot of times it's confusing to people to see this here, the idea that the difference is less than 0, because this is a really big number. So how do we interpret a p-value like this? Well, what we're saying is that if the null were true, and the null in this case is that there is no difference between these two groups with respect to mom worked, that mom worked was the same proportion in the population, we would see a result this small or smaller about 99% of the time. In other words, we don't have any evidence that the true difference is actually in favor of the proportion of mom worked among the upper classes being larger. And that intuitively makes sense because in the sample, it's smaller. So that's not good evidence against the null in the other direction. I wanted to call attention to that because sometimes people get a little confused because it's counterintuitive that a small p-value is good. It's not necessarily good or bad because you should just try to be objective about it. But usually you want to find significant results so you can write it. Paper's easier to write. Yeah, a lot of times people get confused because small p-value being good is counterintuitive. So they see a high p-value here, and usually because we like more of stuff, they think that maybe this is the p-value they should be looking at. But usually you have gone awry in thinking about the problem if you have a really high p-value like this. It means you did not craft an alternative hypothesis in the right way. I shouldn't say in the right way, but it means that you were way off base, basically. Assuming that you have a large sample and blah, blah, blah. But, there's a whole lot of other reasons you may not have significant results that might have to do with the exact specification of your model or again, the sample size, but all else equal, it does mean that you don't have evidence in favor of the alternative. Okay, so that was a digression on p-values. You don't have to do that on the exam, as I mentioned. Most people in the class in theory have been exposed to that, so I do want you to try to do that for your project because that is something people expect. But talk to me if you're having issues with that. So let's try to represent this graphically. Spine plots tend to work pretty well for cases like this. They get a little bit messier when you have more categories, and then there's a whole bunch of alternatives that I showed in the lecture 6.2 file on descriptive statistics. But I'm keeping it simple here in part because you've probably inferred that it's important to know how to transform variables. And so you can probably infer that I'm less likely to ask you to use a polytomous variable or one with many possible qualitative values than I am to ask you to do some recoding. And that's one reason that we do recoding in part is that one, it makes simple intuitive tests like the proportion test, which is more intuitive in a lot of ways than the chi-square test, in part because you need to do a whole lot more work with this. You have to do a bunch of kind of post-test investigation or diagnostics to figure out what made it significant. I showed that last time, a couple of weeks ago when we did descriptive statistics. Whereas the proportion test can be immediately evaluated in a more nuanced way. So there's a lot of reasons to like dummy variables. So let's do a spine plot, and we'll also see that it tends to produce nice graphs. And this is actually quite nice to look at, I think, even if the message is one about certainly the unequal and very likely the unjust state of the world. But still, this is aesthetically appealing, and it's pretty easy to interpret. A nice thing that it does is that it basically is showing us something that's a little bit like a two-way table, but we have, it's kind of like also a segmented bar graph, except the areas of the bars are proportional basically to their overall weight in the sample. So in this case, we can immediately infer one, that popular classes are a bigger part of the sample, which makes sense based on how we defined it. We defined it pretty broadly. We can also see here, though, that it's clear not only that this is the marginal distribution here, but also that mom works in is different among the two classes here. We can also, although we can't directly infer the mean of mom worked, we can say that it's got to be between these two values, of course. So we also get a little bit of information about the marginal distribution of mom worked, and we can say it's probably going to be closer to this. So spine plots are pretty cool. I recommend using them, and you do need to install it. So in the case that you happen to be using Stata on a different computer for the exam, just as a reminder, you can go like this, SSC, install whatever. I'll do spine plot again. Sometimes you'll get an error message that says it's already installed. Usually the programmer, whoever contributed it, has written it so that you don't get an error message. Sometimes you'll get an annoying error message though. I think I've maybe shown an example of that. I can't recall off the top of my head, but it's not a big deal. Then you just don't need to do anything. It can just be weird to get that message. Okay, let's keep moving. So now let's create a table that displays mean values of mom worked by country and class. And this is a way of basically doing something that can be handled in a more sophisticated way. That's often the topic of discussion in 361. But again, because I'm trying to pitch this at a broad group of people that have different levels of statistical experience, we're going to kind of use a technique that we already know how to use and is a little more intuitive to basically look at the effects not only of national status and the effect of class, but also sort of whether the effects of one vary by the other in predicting the percentage of mom worked. And let's interpret the results. So I also said, go ahead and try to format mom work. So in this case, I forgot to put a note here. We just want to restrict the number of decimals. That's the main problem with this. You can see, well, yeah, let's try this first. So I'm actually going to run this first before formatting it, just so you can see. You've probably seen this already in Stata before, but this is kind of hard to interpret because there's just too much information. And in a lot of cases, calculating percentages beyond, say, the hundredths place, hundredths means two spots to the right of the decimal, is just not super meaningful. There are cases where it can be meaningful if you're thinking about, say, incidence of a rare disease or something like that, where the base probability of the disease or the base incidence is very low. So it represents a relatively large increase, even if it's small in percentage point terms. But for things like this, it's generally speaking not a good idea to report things this way. So we can format, let's close this, we can format momworks that displays overall 6 decimals or 6 numbers, and well, 6 characters actually, and then only 4 past the decimal. Okay, so we'll do this here. And we don't see an immediate result, but we'll see it when we run this command again. So let's do that. And here I'm using tabulate, and I'm writing some momworks. One upside of tabulate is that this hasn't changed with Stata 17, which many of you, I believe, are running. You can always check which version you're running by just writing version. So I'm running 16.1 on this computer and 17 on a different computer. Generally, not a lot changes, and usually they don't go back and retroactively change things. They just add things. Unfortunately, table is a case where the syntax changed a lot, the layout changed a lot. Yeah, I'll show how to get around that later. And you don't need to get around it, but if you're a little stuck in your ways or just don't see any merit to changing the syntax, you can always, well, I'll show you, you can use version control to fix that. So with tabulate, when you write sum here, it's going to produce summary statistics for means, standard deviations, and frequencies. Usually the latter two aren't relevant for this sort of exercise. We'll see actually in a moment that frequency is probably relevant when we need to take a closer look. But at any rate, let's look at the basic output here. And why don't I pull up table as well, just to show the other version before we get into the meat of it. So here I write version 16 colon, so this is a prefix, and it just tells Stata use version 16, so Stata can do that, which is pretty cool. And we write table, country, upper class, and then C, and we can just directly specify the contents that we want. So I can just write mean, I don't need to say don't do no standard deviation, no frequency. I believe you write stat here in version 17, but knowing version control is just a useful thing generally. It's one of those Stata utilities that's under-recognized, but pretty cool. So you might as well try out version 16 if you want. Also, the tables do look kind of different. They're laid out in a different way. So if you want to follow how they're presented in Mitchell's text and how I've shown them, you may also want to do this. It's not too hard to go between the two, but it can be a little confusing. So here we see basically the same information. We don't have this total column here, but we're able to add that in with table if we want, but that wasn't necessarily part of our purpose. So we'll just look here. And what are we looking at here? Well, basically it appears that pretty consistently, and we may actually have wanted to have the totals here of the columns, but basically it appears overall, as we saw before, that if you were in the popular classes, it was more likely that your mother worked when you were a kid, and it was less probable if you're a member of the upper classes that your mom worked. Here we see that that effect is mostly not modulated by, say, country's developmental status or anything else that might vary between nations. It's true for most of these cases, but not true for every case. So it's notably not true for New Zealand and Sweden. And one reason for that we might try to think about is, well, those countries are relatively wealthy, unlike some other countries here. So it depends on, basically, the survey was asked in 2009. We don't actually know, we don't have information on the age of respondents, but this is referring to presumably, at least 18, or sorry, not 18, because it was asking about 14 and 16. So at least a few years prior to that. And if the person was not like the youngest age possible for a survey, which usually is for adults, then it was referring to likely 10, 15 years ago, something like that. So some of these countries were, relatively quite poor at that point in time. And so we might think that maybe the relative wealth of the country has to do with that. But it might also be the case too that not the relative or really the absolute wealth is more what I mean, but maybe the kind of relative inequality as well in the country. So the United States, for instance, has had for a long time at this point relatively high levels of inequality. So that could help explain this. This is all speculation. You would want to do much more work and engage with the literature on the comparative sociology of the welfare state to say something about that. But that's one thing that you might consider as well. Okay, so let's check that. Check that out. Let's pop this up and then let's move on. So now we're going to do something that's relatively similar, showing this repetition kind of pointedly to give you a sense that this is important to do on the exam. So now we're going to generate a variable that identifies individuals who completed above higher secondary level, other qualification, which is this kind of funny way that this data set measures education, or something higher versus those who've completed less than this amount. So we're again making a dummy variable here. And I wanted to show one more way of doing this. In this case, we can just directly handle missing values. We're not quite doing it directly, but we're basically making it a little more explicit what we're doing. So we describe degree, we get the label list. We see that in this case, we want for people who have above higher secondary other or just a university degree, we want people above 3. And in this case, we can specify and not missing. So we use the inequality operator here. Then we replace this new variable GT secondary if they are missing that variable degree. We tabulate here just to check our work. And we see that this looks pretty good. We can assign a value label. Checking your work is really important, by the way. I've already shown it in this re-recording, but I don't mean to disparage it or anything. Do make sure to do it on the exam and in your papers and in life. So we knock out number 9 pretty quickly because that's all we need to do. And now what I want you to do is display means on GT secondary by country and class here. So we're going to, basically do the same kind of operation. And it's just good to get practice because, again, this is simulating in a way that's kind of simpler and more straightforward, an operation basically using qualitative predictors to look at an outcome that is either quantitative or semi-quantitative, as in the case of a binary outcome like this, because we converted GT secondary to what is a dummy. It simulates a way of doing things that's really common at higher levels. So we can again take a look at this after doing some formatting. Notice that we can change the formatting for multiple things at once. And in this case, I wanted to call a little bit of attention to something we kind of glossed over before, which is that the upper class is not a huge number of people. And so it might actually be meaningful. Sometimes you may not want to publish or put into something you submit for a project frequencies if they're not meaningful. They don't tell you anything, but here we actually do see that people in these upper class buckets using a rough cutoff of like 1 to 200 people as a good guideline for what's big in statistical terms, that's really, really rough. There's a lot of different ways to think about that. But just in terms of thinking about, am I going to see a case where despite notable differences in, like this is a notable difference between popular and upper class people, the mean of GT secondary, right? The percentage points are, almost 8 percentage points, which is not nothing, considering that only 100 percentage points are possible. We might still fail to see statistically significant results because of these small differences. So that's one reason to use that rough cutoff. So we do see that there appears to be this overall difference, right? In general, it's pretty pronounced in the United States, pronounced in Sweden, not as much in New Zealand, pronounced in Korea, not as much in Japan, very pronounced in Italy, and by far, educational inequality was most attenuated in China. So what I wanted to show you here, this is an advanced topic. I do want you to think about doing something like this for your projects. If some of your categories are small, it's not necessary for the exam. So what this shows here, I've shown a way to do this by hand before that's a little more involved, but what we can do is just run the proportion command here, which will basically show us proportions of GT secondary over country and upper class, which is basically what we did with this table, except it's going to give us confidence intervals. And so we write percent so that these are reported as percents, which makes them easier to interpret. And we use the confidence interval type walled, which is not actually the best performing confidence interval. but it's the one that corresponds to what you probably learned by hand in your intro stats course, and so I will choose to use it. And we can look at this table here. Now, this is a little hard to look at, although there's a lot of commands you will learn at higher levels, like margins that I sometimes show in these lectures that looks a lot like this. So don't feel too intimidated. I'll show you kind of how to pick through it. Let me call attention to an example that I called attention to in class, which is for people who are in China who have post-secondary, because that was the problem category we identified. And let's look at post-secondary education havers, basically like the proportion of people who have post-secondary education in China for the upper class. So the raw percentage in the sample is 22.73, as we saw before, but a confidence interval with the standard, although it's arbitrary, 95% confidence, has really large bounds. So it could be as low as 12.62%, using a method that works to include the true population parameter 95% of the time. If we were to iterate it, which we don't ever do in practice, at least unless you're doing something like bootstrapping, but it's just kind of the theory of it. I've shown that before. I won't get into the details. Actually, it takes a while to go through. But basically, it's between 12.6 and 32.84% with a pretty high degree of likelihood, which is a big band, right? I mean, this is pretty significant. Again, considering that these are percentages, this is a lot of variation because the maximum, the range is of course 100. So we have to be a little bit careful here, right? You might notice, although this is not actually something you should do, you shouldn't evaluate things this way in practice because it's not very rigorous, but just as like a brief spot check, notice that the lower bound is actually lower than the lower bound for people in the popular classes, which tells us something that, these estimates are, we're not getting a whole lot of precision here. You can also do something that's a little bit like a loop. Again, you don't need to do this on the exam. I want to make that explicit. But this is just a way of dealing with a problem that is not obscure and not, and especially like noticing that having really small categories is problematic doesn't require you to have like really deep statistical knowledge. It's something that hopefully feels sort of intuitive. So what we can do is, for instance, run a set of proportion tests by country. And this reminds you what the BISWORT command is, which is something that is often used, and it's often used in our course. Basically what this does is tell Stata to iterate the proportion test of secondary education by upper class over country. So this is like a loop, except you just don't have to know as much about the programming lingo, which is nice. We could do this with by without sort, but a lot of times we're going to get this error message. I'll just show you what's characteristic. It tells us that the data aren't sorted. So the data are not currently sorted by country. So if we just write by sort, that also sorts the data by country. And then we are able to get this set basically of commands. And so the thing I called attention to in class was that if we go up and look at the case of China, for instance, assuming that we're doing the more conservative two-tailed test and using the standard, although arbitrary, alpha of 0.05, or basically 5% chance of seeing results this extreme or more if the null were true, we actually, by that standard, fail to reject the null hypothesis, although just barely. Using alphas is actually, I think, bad practice. It's something that should probably go into the dustbin at this point, and you should just say what the p-value means. We would see results this extreme or more, so either in the upper or the lower tail. Only about roughly 9% of the time with rounding, if the null were true, which is still pretty small, but it means that 9% is not an extremely rare event, right? 9% of people are left-handed or whatever, just to use a kind of a rough, familiar example, something that feels intuitive. So we can certainly say that we have small evidence against the null here, that there is no difference between these two groups, that popular and upper classes have roughly the same levels of education. Whereas if we look at all of these other cases, these p-values technically aren't zero. It's actually impossible for them to be zero because, again, for a probability density function, it never actually touches the x-axis. So there's always some area under the curve, and those functions represent the sampling distributions, but the area under them can be effectively 0 and state around it to 0. So we see all that here. So all these other countries, there's very strong evidence against them all that the two classes that we defined have the same educational levels. Okay, so that's just a point worth noting. And it reminds you of how bisort works, which is generally pretty useful. It's useful in a lot of contexts. So I probably raced through that a little bit in class, but hopefully that gives a sense for what you need to do on the exam. You don't need to do this, but it shows you how you could think about some of these problems in your paper if it comes up. We might also see things like this in future homework. And generally speaking, bisort is the kind of thing that will also keep coming back up. So now let's go ahead and transition, and I'm going to pause the video here. What we're going to do next is look at the CPS from 2019, and we're going to look at basically some more quantitative variables. So I'll see you all in a bit. All right, folks, so let's continue with the second part of the review. This will be focused more on quantitative variables. We'll do a lot of the same things, and we'll do a few things that are a little bit new. So here I suggested that you load the CPS 2019 and construct a variable indicating whether someone has any children. So I showed basically the process of making a dummy variable here. We've seen this a lot so far. Again, that's a strong hint that'll appear on the exam. I used the true syntax here, and I showed a simpler way of doing things we've already seen above. But I also wanted to show something that could come up as maybe a challenge question on the exam, which is, what if we had information that's just encoded in the variable ch? So those that start with ch. So let's look for child, let's say. And notice that we have this variable own child, number of children, but if we didn't have access to that variable, we might only have access to these other ones. And as I noted in the lecture here, basically, this comes up a lot in the real world, where it might be the case that a survey just asks someone information about things in a way that was maybe a little short-sighted, and you have to do the best with what you have. So how could we use what we learned about eGen to calculate such a variable, basically a dummy variable? Well, we already did this. We looked for the variables that work, and we see that there's a common pattern here. These all start with ch. And so what we can do is run an extension to generate. So basically just generate with some fancy stuff. Let's call this one isParent. We called the other method hasKids. And we want to take the row maximum of any variable that's got ch and then has characters after it. And there's different numbers of numbers here, so we want to be pretty general, and we'll just use an asterisk. So this is kind of a funny method, but it works. I'll just show that it works first. And you can see here that we have the same thing we got from doing the canonical way. And we, just to show this one more time, I probably should have lingered on this a little bit longer, but hasKids does work as well. We look at how this is constructed. And so what did we do when we used this eGen method? Well, if we look at the set of these ch variables here, and let's do this. So we can come here and we can write tab 1 like this, and we can look at all of these different variables. Notice that this is a set of dummy variables that indicate not whether someone had kids between this age, or how many kids they had between this age, because presumably we would to see many people that have 0 to 5. There's got to be a bunch of people who have like more than one kid in that age, right? So notice that this is this kind of interesting set where pardon me. And it's overlapping too. So we have kids 3 to 5, kids 0 to 5, kids 0 to 2. So that's information that's really hard to uncover. It's really bluntly recorded information that's not easy to convert. But if we're just looking to see if someone has any kids, one way to think about this problem is basically assuming that, we're one thing we're abstracting from just incidentally is we're not worrying here about people who have adult children. That's sort of a problem with the CPS, that it conflates these two things. So that's more of a problem you would want to deal with in the real world, but that's not the focus here. But basically, the way we're thinking about this is if we just want to see if someone has any kids at all, at some point they should have a 1 on one of these variables. And so if they have 0 on all the others, even if there's a mistake, like they have, a 1 on child 0 to 5, but they don't have a 1 on either of these two, which would be a mistake. Um, it is the case that they'll still show up. And that's why our code kind of works here, because it's very inclusive. Conversely, in order to have no kids, they have to have a 0 on all of these things. And then and only then will the maximum of these variables for them be 0. Otherwise, even if they only have a 1 on one of these things, that's naturally going to be the maximum, of course. So this ends up working out very nicely. And we can label the variables as well, and then go ahead and show that they produce the same result. Okay, so that's that. Now let's talk about how the gender wage gap for hourly workers relates to parental status. So we're going to first fix the variable female on the GSS, which is for some reason, or CPS, pardon me, which is for some reason not labeled in the extract we have. It's a little annoying, but that's okay. And we can do this with a table again. So although we don't have the easy ability to do inference here, it's still totally fine to use this method on the exam. So let's look at a tabulation of female and its parent, and then we'll put wages in there as the contents. And so if we look here, we can see we've got on the variable female, again, the CPS uses the sex binary. I'm not saying that that's ideal, but it is the nature of the data we have at hand. And this is one of the most widely used data sets. So I want to show you something kind of realistic, although it is certainly problematic. And we've also got the variable we created is parent here. We could just as well have used has kids, same difference. And we see here, we've got the values no children and has children. And so these are conditional means. These are 4 conditional means. So conditional on being male and not having children, here's your mean. On male and having children, here's your mean. Female and no children here, and then female and has children, here's the mean. So what pattern do we see? Well, this is actually quite fascinating. And I'll show a graphical representation in a moment. You can show this in a variety of different ways. You could show a bar graph here, for instance. And I show some ways to do that in the pardon me, in the lecture on basic descriptive statistics. We actually could show that if we wanted to here. So we could say graph bar wage 1, and this will just calculate the means over female over is parent. And you have to play around with this a little bit. This may or may not look that good. Just wait for this to pop up. We see this doesn't look too bad. So we see here, we get a sense of basically among groups of people that don't have children and have children, how does the effect of being male or female change? And we notice that for the people who have children, the gap does seem to be notably larger. We can also change the order here too if we want. And this is a rare case where changing the order of options matters because it determines which is sort of like the super category. And sometimes you have to play around with this and look at it and see, well, is that really what I wanted to take a look at? And then here, this actually is an easier way to look at what we were thinking of, because now we condition on male and female before we condition on children and no children. So there's this really interesting fact that we saw in the table, but this is a little bit easier to see. For men, no children is associated with a lower wage than having children, but for women, it's the reverse. So it's actually not just this data set that shows that, but it's actually a pretty common finding in the literature. Let's paste this in here, and I'll show this here. There's also a way to do this with table that we saw before. I discussed the difference between these commands and some of the version control material earlier, so I won't belabor the point there. And let's say here is a very simple graphic method for seeing this difference. Put that there. Yeah, so table, in this case, we can easily add a column total here and look at the overall effect. And one thing that's pretty noticeable here, we also have a row total, is that there really isn't much of a difference overall between not having children and having children. This is a pretty small difference, right? So this difference is about 50 cents on the dollar. This difference is also roughly around 50 cents, a little bit less, whereas this is, right in the realm of like cents basically, and maybe even a little different than that. So not a huge difference. I mean, these are all small, but if you really think about how fast they're going to add up, these differences here, conditional on gender, are more significant than the overall difference. So that's a way to visualize this and see what's going on. You can do this with regression as well. I'm going to pass over this lightly. Basically, what you would do is use the interaction syntax here. When you fully interact a model, it basically is like running a separate regression for each group you're grouping on. So if we look here, we see we're regressing wages on female, on is a parent, and then on the interaction of the two. So we can calculate from doing this basically 4 conditional means. So if female is 0 and is parent is 0, this will also be 0. That gives us 1 conditional mean. If female is 0 and is parent is 1, then we just have basically this term in there. I'm being imprecise, but you can write these out if you're used to calculating conditional regression equations. And then this is also 0, so those terms will be different. If female is 1 and this is 0, we just have this term in there because this is also going to be 0. That's a third distinct term. And then finally, if female is 1 and is parent is 1, then this interaction term finally appears. And so then we have a fourth distinct term. We also don't need to calculate those conditional means by hand. We can use margins to do it. And margins here will identify. These we don't really want to pay too much attention to. They're main effects in a model with interactions, so it's hard to say that they really have much meaning. But we see here the 4 conditional means, and these 4 conditional means, 21.9876, 22.4590, 18.7239, and 18.2808 are the 4 conditional means from our table up here. So 28.9876, I won't bore you with the tedium of reading this out, but basically these come to the same thing. We can also use margins plot to plot these margins, and this is another way of visualizing what we saw before. This is not available easily. It's possible, but it takes a little more work if you don't know regression. This is just another way to see this. And this has the nice effect that basically we look at the effect of having children conditional on being male. So a slight but noticeable increase. These are confidence intervals, by the way. For being female, pretty noticeable decrease as well. And then this is the overall effect, which technically speaking, I actually don't even know which way it goes. I'm having a hard time seeing. It's very minimal. So the minimal, basically unconditional effect masks a significant conditional effect. Okay, so that's that. Again, you do not need to do this on the exam if you don't know it. If you do know it and want to use it, that's completely fine. You can also use this. Just laying the options out there. I know there are people in this class who have already had to take 361. So in theory, this is review for you. And I'm just showing you that you can do it this way if you like. Some of you may be in 361. I can't remember if that's true or not. Some of you may have taken it a long time ago. Okay, let's now look at the next question. And this is going to be quite similar, but I'm going to ask you to show another graphic method. We saw here, this is one way using bar graphs, but now I want to look at a continuous predictor. So I want to see whether the effect of education on wages differs between non-white and white workers. So first we need to make a dummy variable for whites. We're doing this yet again. And what we could do in this case, we can just use the race variable as is if we're just calculating a few conditional commands. So if we look at the variable white, black, Hispanic, other, which is the simplest race category, the CPS actually has some better ones. If we look here, let's come back. Here we can kind of see this set. We could also use plug in race and see here. But we don't really need to worry about the fine detail because we're going to make a dummy anyway. And since we might be interested in the structure of white supremacy or white privilege in the United States, maybe that makes the most sense to just stick with a simple one, even though it is obviously on some level always problematic to pool people. So let's look at the value label. And we can list that and see that white people here are coded as 1. So if we want to run a regression for whites, we can do this. And this is something that is not hard to understand. It looks like there's maybe a lot going on here, but this is just single, or not single, but bivariate regression. but just with a conditional statement here. So this is just running the regression of wages on education for whites only. Let's take note of the coefficient. So it looks like for a unit increase in education, this is actually not years, strictly speaking, because the CPS doesn't measure education in years, which is cheating a little bit on my part, but don't worry about it. I won't ask you to decide something that specific on the exam. So if I tell you a variable is quantitative on the exam, you can treat it that way, even if it, maybe is really more ordinal. So the coefficient for a unit increase in education is, about $1.79, $1.80 an hour in terms of your wages. Constant usually is not meaningful because in this case, having a zero value of the predictor is unlikely, but we'll see that the difference in constants is kind of interesting to look at in a moment. Let's look at the regression equation for individuals who are not white. And now we see that the coefficient is significantly different. It's just about $1.05 for a unit increase in education. So, again, small numbers, but if you're thinking about the substantial meaning, and it's not hard to interpret, right? It's actually, these are just cents. Because the outcome is dollars per hour. So cents per hour, that's not meaningless for sure, right? I mean, I think all of us wouldn't mind getting, basically a 75-cent increase in our wages hourly. It's not a lot, but you wouldn't turn it down. So it seems like that's reasonable. That's enough reason to say that this is significant. That's all you really need to do on the exam. So you don't even need to make a dummy variable here. Now, how could you do this using some of our techniques that we've seen before? Again, we could use tabulate and then generate. And again, I'm just showing this because we've learned most of this already, and it is kind of fun to see what you can do. And it's faster in some ways sometimes. Not here necessarily, but if we were going to use this variable much more, it would make sense to make a dummy variable at some point. So let's go ahead and we can use the same method. I've already shown this. It generates a set of dummy variables here. So these are all white. They all started with the word white. So why did I call it that? Well, we're planning to drop these other three in a second because we're interested in the difference between white and non-white individuals. So this is also a way of seeing all of them. And we're going to just keep the one we're interested in. So we rename white 1, which happens to be the one where 1 means white. We're going to rename that is white. We'll double check our work. And this looks pretty good here, right? Apparently no one was missing on the race variable. A lot of times it's information you have to have or else you are excluded from the survey. We can make a value label and apply it. We've already done this. Now I'm going to show you how to use loops for all the other dummies. This is not necessary in this case, but loops are useful in general, and it's kind of nice to see how it works in a simple case. So here, and again, you don't have to do this on the exam. You may find it useful in the homework, and we are going to have a week on programming. So it's not, I know I keep justifying why I'm bringing these things up, but I guess a common critique I've gotten in the past when teaching kind of more foundational courses is that I tend to bring up a lot of irrelevant material, but I'm trying to make the case to you that this all kind of hangs together. And even if I'm saying I'm not going to force you to do this on a midterm, I'm not that mean of a person, we are going to talk about it eventually, so you might as well see it. This video is timestamped, so you can skip past this if you want. So we can use this loop here. So how does this loop work? Well, we write 4 values, and basically what this says is for values, some variable. This isn't a real variable, it's just going to exist in this program, this little micro program here. But what we're doing is common sense, so don't overthink it. We're just telling Stata for values I in the set 2 through 4. So every time I is 2, 3, and 4, we want to drop white with an I on the end. So basically this is telling Stata in so many words, drop white I for I equal to 2, 3, and 4. So drop white 1, or sorry, drop white 2, drop white 3, drop white 4. And that's kind of what we wanted to do, right? So let's keep an eye on this in the background so we can see the result while we do it. And you can see we eliminated all of those others. So that's a basic loop. We've seen some before. They're kind of fun. They can be hard. They require a lot of toggling. We'll get to it later. Once again, we can run a fully interactive model. I show some material here on how to test basically these effects. I don't think you should worry about that even if you know multiple regression, because testing these things is tough on the exam. You can wait to try your hand at that on the paper. Okay, so how can we represent this graphically? So there's a lot of code here, but I just want you to be able to understand the basics. You can definitely just copy portions of this in the exam. So don't memorize this, bookmark it, and just make sure you understand why I put stuff where I do. I'm going to explain why I do that. So let's start with the basic syntax. We know what we do to do a scatter plot. We write scatter y value, x value. We can write a conditional statement. It's something you can do for almost any command. And then we write jitter. And why do we do jitter in almost every case? Because otherwise the graph looks really columny. And I'll just show that briefly to illustrate one more time, even though you've seen this before. I'm not even going to fit a regression line. I'm just going to show. So why are we seeing this? It's because education can't take on non-integer values. Actually, a lot of scatter plots you see out there in the real world have some kind of jittering. And the reason for this, as I explained before, is that we can't actually see the height of these things. Like, it would be great if we could see in 3 dimensions, because then we would see, oh, there's actually tons of observations that are stacked on these dots here, probably not here, but more like around here or something, actually much more probably around here. And there's probably not a lot of observations stacked around here, certainly not over here. But when there's only a limited number of possible values, possible coordinate pairs, it's a little hard to see that. That's one reason why I'm going to use a contour plot, although contour plots are finicky with regression lines. They also don't look so good with regression lines. Contour plots are fun. And in fact, that's what's on the homepage of our course. It's a contour plot I made just to show you something kind of cool when I was setting up the course. But yeah, so this looks kind of columny. So we always want to use that jitter option, which basically puts some random noise around especially dense areas so that we can kind of get a sense of where there actually are more observations. And then we can just add plots together. So we can just add these double pipes here. Single pipe means or, but double pipes just let us combine commands. So we do that here. You can't actually just use the forward slashes here. I think I mentioned this before, but when we're overlaying plots, we need to also add these. Basically, this joins lines, this joins plots. So then we just do another conditional scatter plot with white equal to 0, or is white equal to 0. We also add a jitter. Now we want to add 2 more plots. One is a line of best fit for people who are non-white, and I just switched the order here. It really doesn't matter too much. It probably would be more consistent to put them in the order of 1, 0, 1, 0, but this is fine too, as long as you just keep track of it. And then we put finally a line of best fit for wages and education if people are white. Then we add a title, and this is added as an option to this LFIT plot here. You could really add it to any of them because they're all being overlaid, but it's simplest to add it here. So I write X title, and this just puts them on the X axis, called it education. Defaults are oftentimes really not informative. I write Y title, I call it hourly wage because that's what appears in the Y. I give it a title, call the effects of education upon wages for hourly workers. I don't mention race because otherwise the title would get kind of long, and because the legend, which we'll come to now, also makes it clear that we distinguish between race. So the legend goes like this. There's a couple of different ways to write them, but it just appears as another option. And you can change the order of these things, but generally speaking, the items in the legend correspond to the order that you put things on top of one another here. So first we made a scatter plot for if people were white. So the first element will be white. And you can always look at what this looks like and then go back and change it. The second one is for non-white. So we go look at this. Then the third one also, as I mentioned, was out of order. So I stuck with a line of best fit for non-white people. So I made that non-white as well. And then a line of best fit for white people was the fourth element. So I do that here. And let's take a look at this. This is definitely the most you need to do for the exam. And I will consider it, even if you just run something that's as simple as not having the legend or the titles, just put the jitter together and put these plots together. I'll give you a strong majority of credit for that. But this is what this looks like, and this looks a little bit better, right? You can see one advantage here of plotting the scatter plot that's got less variance, which in this case it's, pardon me, for non-white workers. You can see the advantage of plotting that group second, because then that allows us to see the difference here, where there's more white people up here. You can see the jitter makes this look a little bit less columny, although it's still pretty bad. But if we make it much thicker, it's going to start looking like a giant blob. So we don't want to do that either. There's a trade-off. You can see the key is also a little bit nicer, and these colors are maybe not the best. There's ways to toggle that, and I show that soon. But this is, this definitely gets the job done. Pardon me. That's basically what I explained here. And here's something you might want to try for your project that you don't need to do for the exam. So let me just show you the product to motivate this, because the product ends up looking kind of cool. And basically, there's a lot going on here. What have I done to make this maybe look possibly more appealing? Well, I've changed the size of the objects. I've made it a lot smaller. I've changed the shape here, so we have triangles and circles. I've also made the colors a little bit more, maybe a little bit easier to distinguish. I actually don't love the way that this renders, but something to play around with. I've also made it so that they're almost entirely translucent. So in fact, these are hollow, and they're also translucent on top of that. So it's easier, much easier to see what's going on with this overlay, unless they're both really dense, but then that's also information that you want to have. But where there's some distinction, you can see there's a lot of granular detail here that would be left out, certainly by that first kind of scatter plot we looked at. I also elected in this case to, instead of dealing with lines that are different colors, because these color schemes can be really funky, I just thought it might be easier to use different kinds of patterns here. Maybe you want even a different pattern. And I'll blow this up so we can see it a little larger, because this is easier to see. Sometimes you want to make the graph larger. We also have the titles and things, but I've also changed the pattern here. So how did I do all that? And this will take a second because there's a lot of information for that. So how did I do all that? Sorry, I had to hide the meeting controls here. Well, basically, I wrote scatter as we did before, but I also changed the color of the scatter plot. I wrote red, which is just the default color in Stata, and you can use help. Which one is it? Yeah, help color style to learn more about that. I also use the percent sign here, which makes it translucent. Basically, this is like telling you what percent of the actual color to show. I wrote jitter as before. Again, the order of these options doesn't matter because they don't affect one another. And I wrote M symbol, and I wrote OH, which basically just means a circle that is hollow. The O is basically for circle, H is for hollow. I did the same thing for non-white folks, again, making sure to put them second. I used blue, and then I wrote TH for hollow triangle. And then for the lines of best fit, I just changed the line pattern and the color. So I made both of them black because it's not the default. And then I changed the pattern to short dash dot. You can learn more about symbol styles and line patterns here. And then on the legend, I basically did the same thing that I did before. And I used the same trick again of using the limit changer to make this a little bit easier to write and not have to write a bunch of forward slashes here. Titles also are especially hard because you really can't split them over lines. So it's best practice to not have your lines spill really long. So this is one benefit here, is I don't have to write additional characters to do that. Okay, so you certainly don't need to do that in the exam. You may want to think about trying to produce something like this for your final project. It's pretty cool to look at. Okay, so that's that. Let's talk about the last couple of questions here. So number 14, create a dummy for Scandinavian birth. Use the restricted definition for the sake of time. So this is yet another dummy variable question, but this one's a little different. And there's a few things to note here. One, if we do the describe, we see that the variable P nativity, which basically is the country of birth, has a value label that doesn't fit the pattern that we've seen so far, which is that it's directly related in a pretty simple way to the variable. So that's one thing to watch out for. Then we want to look at the label list, and we'll see the second thing. And the label list is really long, and it's a lot to look through, right? So if we want to use this restricted definition of Scandinavia, let's try something simple that you all are probably pretty familiar with. Let's just use Control F. We can find it on the page. So we write down that Sweden is 136, Norway is 127, Denmark is 106. It might seem like a strange definition of Scandinavia, but I guess this is the local definition. I'm actually not able to verify that, even though I know some Scandinavians pretty well. I probably should ask them first, but that was what I heard on Wikipedia, and I just used it for the sake of time. It's easier to write down 3 countries instead of 7 or whatever the broadest definition might be. So we can kind of do the same thing we've been doing. We just have to be a little more careful, and I thought it might be worth showing this. So here we say gen Scandi birth equals, and then we write down p nativity equals 106, 136, or 127. And again, this is going to use that truth syntax. So it's going to give people 1 if any of these is true, and it'll give them 0 if any of them is not true. And we should also basically make sure that we don't have any missing values. So I actually neglected to do that here. Let's check that out. And we actually don't see any missing values. So this might be another case where, oh, but what we should actually do is look at p nativity. Sorry. Some commands won't do that naturally. But it does appear that no one has any missing values on nativity either. That's actually really interesting. What we could use is use the missings report that we saw before, which I introduced to you. Oh, it's in the lecture itself. So let's do missings report. So take a second. And if we look at this, this is a lot to look at. We can again use Control F. And we don't see anything. So it appears that even though it seems like there should be some missing values here, this might be other information that everyone had to answer. So that's worth pointing out. The reason I thought to check it suddenly was that it can be the case that some true syntaxes we saw before, sometimes this will evaluate missing values as being 0, even though that's not really the right way to do it. Okay. So I'll put a note in here explaining that. But now that we're confident that we've done this correctly, we can define a value label and then apply it. And it's kind of hard to check our work here. Or when I said we were confident we'd done it correctly, I meant we didn't make that mistake, but we need to check for other kinds of mistakes. And this is a little bit tough. So if we do what we normally do, let's just show this. It'll look like a total eyesore, but it'll make a good impression. This is kind of a lot to look at. It could be worse, but it's easy to see that we could make a mistake, right? I'm scrolling up and scrolling up and scrolling up, and it's really not that easy to evaluate. So one thing we might want to do, it's not actually as massive as we might have feared, but especially if we had more than a couple of values here, it doesn't look great. So another trick we can use, and this often works, is to basically tabulate by Scandi birth. So basically for the 2 unique values of Scandi birth, we can tabulate nativity, and instead of putting anything in here that's intrinsically meaningful, I'm going to put the percentiles. And why would I do that? They don't have any intrinsic meaning because they're qualitative variables, but you'll notice that when I do that, we get a sense of what the range of possible values are. So we're going from 1 to 25 to 50, 75 to 99. So probably we have a good chance of capturing values in here that are typical to appear. Notably, for born elsewhere, you'll see almost all of these are 57. That's the United States in the CPS, and that makes sense because we're going to have a fair number of people who are born in the United States. We don't have a, we have a sizable immigrant population, but it's not so massive that you're going to see 50% of people or something like that. And then this 99th percentile is really not intrinsically meaningful. It depends on the ordering of the variable values, which is arbitrary. This is also useful though to look at Bourne scale data. So we only see values 106, 127, 136 in here. And we might remember that those were the three numeric values of Denmark, Sweden, and Norway. So we're also probably in good shape here. And this isn't intrinsically meaningful, but it basically just kind of samples throughout a wide range of the distribution. So I'm going to consider that probably done accurately. Let's also take a look at this situation of looking at weekly pay and checking whether or not we might have any problems or inconsistencies between a dummy variable and a continuous variable. So let's see if someone has surprising results. So let's make a dummy variable called is paid weekly. We've done this a lot. And we'll label it. I'm not going to go into too much detail here. And now let's come to the meat of this. We want to see if people who are paid weekly or do not have weekly pay, what their mean wages are. So this is kind of like what we did before, but we're not hoping to do a causal analysis as much as check a variable here for inconsistencies. And quite interestingly, for people who are paid weekly, they certainly have a higher wage, but people who are not paid weekly have some wage, and it's actually a legal wage, so it's not even that small. Now, we might think, uh-oh, have we made our variable wrong? Did we do something wrong? Well, first of all, we can always, well, we can't actually easily check it in this case. In fact, what we're doing is almost a way of checking it. But don't despair, because remember how big our data set is. Probably should have used the short option there. But if we scroll to the top, remember how big our data set is, 290 some thousand, or basically almost 300,000 people. We only have 49 people here, right? And there's not that many people that had an hourly wage recorded, but it's still, this is a tiny, tiny, tiny share of the total. So that's not too big of a deal. And we might think, okay, we're probably gonna have about that many errors outright in this set. So let's investigate a little bit further, and let's just tabulate the wages if is paid weekly is equal to 0. Normally not a good idea to tabulate a continuous variable, but when you have only a small number of observations, it's gonna be okay. And we see here that the plurality of people actually recorded a 0 value. So that kind of makes sense, and probably just means that people misunderstood the question. Like, they aren't paid weekly, and it could be the respondent or the surveyor, they aren't paid weekly, but they knew that they should record 0 income for themselves. So they put down $0 per hour, which is obviously not legal. They could be employed under hyper exploitative conditions, but it seems more likely from context in this case that they probably are just meant to write down 0 some other place. We do see some other people that have interesting values, though. Some values that seem somewhat odd, especially these 101 specifically. That's awfully specific. Notice that there's nothing else that specific. Who knows? This. But otherwise, these all seem pretty plausible. And so we may want to just consider dropping them, even though that's maybe not fully justified in the sense that these may not be a random sample from basically from the overall setting of people, but we may have no better option because it may not make sense to include these people, since we can't decide, is the weekly pay thing a mistake, or is their hourly wage a mistake? But that's pretty much all you need to do for this. Finally, coming to the end here. So I want you to also think about visualizing the overall difference in distributions for white and non-white individuals for wages. So there's a lot of ways to do this. I'm going to show you one way here that you can use on the exam. It's very straightforward. I do use a local here, which I've mentioned before. It doesn't really need to be used, and I'll show you how to do it without a local in a second. But what this does basically, and again, remember this is a command we need to run as setup, and then in the command itself. First, we define the local, and we don't need to do anything other than just write local, the name of the local, what we want to go in it. It can be a string, it can be a number, so on. In this case, we just want to use the title because the title is kind of clunky, and putting it in a single letter makes it easier to see what else is going on. And then what I want to do is graph box wage 1. This is going to produce a box plot of wage 1, and I want to write it over 1. So basically non-white folk and then white. We're going to give it this title. So this, and it turns out that for a lot of these settings, the default title by Stata, if you're doing basically comparative box plots or comparative many things, the size is kind of big. So we simply write inside the title parentheses, size medium, put that in parentheses, medium is usually a good option, and then we write a second parenthesis to close it. And that will look like this. This will take a while because it is a large data set. But finally, we see here, this will take even a little while longer to load. Tends to take a long time because this takes data a long time to produce. But basically, we have a difference in the distribution. We can see, generally speaking, that the IQR is bigger for white people. We saw before that the variance was larger. Those two things are going to, broadly speaking, be in a state of consistency with each other, not inconsistent, but consistent. We can see here that the median's a little bit higher here as well, notably so. So actually obscured a little bit because of the scale. We can see here that, pardon me, they both have a number of outliers. It's kind of hard to tell. But if we consider like what the cutoff is for non-white people because of the overall greater compression here, it's going to be smaller. So some of this is not somewhat misleading because the IQR is just smaller. So the 1.5 times the IQR plus the 75th percentile, which is what's happening from here to here, is smaller. But this gives us a good sense of the distribution, right? We can see the title here, looks pretty nice. We can see the y-axis title here that was provided by Stata. Notice that we didn't have to do anything to call that up. So that looks kind of neat. And that's really all you need to do for the exam. You can do some other things too, and I'll show some other alternatives here. Notice that a couple of things. One, the first file, when I showed this in class, had names for these appended, so I could open them all at once and compare them, but I think that was just adding too much, and it was kind of a pointless, well, it wasn't pointless, but an unnecessary programming detail in the setting. Notice that you don't need to use local to do this, so you could just write in the title. It looks like this. And you would just need to use a little more space. You could use a violin plot or viaplot, as it's called in Stata, but it's kind of slow with such a large data set. The basic syntax is given in the descriptive statistics lecture, and it looks a lot like this because it almost is a box plot. The original file had a quantile plot. I've shown those before. I actually showed those on 360 because people love to use them. They come up really early on. But I think, I forgot to finish this thought, but I think it might be better to omit this here because it is a little bit hard to interpret. It takes a little bit of practice, so no need to worry about that now. Try it in your paper if you're interested. You can also do a two-way kernel density plot. Histograms are kind of harder because they tend to overlap pretty badly. I do show a way to use transparent bars, but you might consider a two-way kernel density plot. And this is something you could also try in the exam if you want, if you feel comfortable with it. It's really not too much more complicated than the box plots. So let me show you what's going on. Here in this case, we need to use the two-way prefix, basically telling Stata to stack these. Sometimes you need to use that, sometimes you don't. You can always write it in front of a case where you're stacking two graphs. So in this case, we do need it. We write two-way, then we write the first kernel density command. So this looks very much like our conditional commands above. K density, wage 1, if the person is non-white. K density, wage 1, if the person is white. And that's really all we need. All the other stuff is just window dressing. So we want to put the order on the legend. So we're going to say non-white workers because they came first, then white workers because they came second. And notice that the numbering starts with 1, not 0 here, even though numbering sometimes starts with 0 in other contexts. We can add a title here. Y title means y-axis. title overall means just the top of the graph. And then we want to change the size again, because if we look at it, it looks a little bit messy, and changing the size is pretty simple. So let's see what this looks like. And the reason we use kernel density here is because they're just lines, so it's easier to see a difference than if we had bars, basically. And this actually looks kind of appealing. We do have this annoying thing that we forgot to change, or I didn't change, which is the x-axis title. You could just change that with x title. But otherwise, this looks pretty good, right? We see for non-white workers, it's clear that there's a greater concentration in the lower end. And for white workers, we see there's fewer people here and more people kind of spread out up here. So this is also, again, kind of a sad story, but it's nice to look at. It's aesthetically appealing to see how this looks. So this is pretty helpful. There's a couple of fancier things you can do for your projects if you're interested. The code gets a little bit longer, but I will explain what's going on here. So one thing you can do is do a histogram, which maybe is in some ways a little bit easier to interpret because it's, well, there's just more to look at. They're not these little thin lines. So we do the same sort of thing here. We do a two-way plot, and then we just write a conditional histogram. So histogram wage one if the person is not white, and we're going to add that translucency trick for row 4. And so when we're overlaying stuff like this, you generally speaking want to make it pretty light. So here we're just telling Stata only print 30% of the color, basically. And here I add the title to this plot, but again, the place you put the title doesn't matter because they're just going to be overlaid. I guess don't make two titles. And we give this title here. Then we add the second plot, histogram of wage one if the person is white, and we pick a different color. And then we just put the legend here. And I'm going to delete the name because it's not relevant for what we're doing here. And let's look at this. And we'll see that this actually looks, again, like kind of nice to look at, again, despite the information that it's encoding, which is unpleasant. But we can see here the translucency kind of turns out nicely. It almost has a stained glass character to it. And we can see it gives us a good sense of where these things overlap, but also where there are differences. And you can also tell, obviously, how this would be quite difficult if these had the kind of standard off yellow bars that Stata gives. So this is much nicer. Definitely something that if you look at the code here, there's really, you don't have to try this on the exam, but certainly if you play around with this for 15, 20 minutes, you could definitely get this. And I think for most people, it would take less time. So something to consider for your paper for sure. Here I just explained what I did above. Finally, here's one last way to do it. And this is maybe the fanciest method, but I'm going to show you it because it's kind of cool. So what we're going to do is basically we want to use kernel density plots, but what we want to do instead is actually fill them in. So we're going to almost simulate these like stained glass textures that we saw, but we want to make a smooth probability density function, basically, or an approximation thereof, rather than having these bars. So we're going to kind of combine this with the kernel density plot in the normal sense to give something that looks like overlapping probability density functions, which will be cool. So here's what we do. We first run a kernel density conditional command. So for non-white workers, we're going to generate two coordinate pairs, or coordinate pair, pardon, so just two coordinates. And what we call them is irrelevant, but I'm just going to use kind of standard math names. So an alternative to x and y, which can be confusing in some settings, could be P1 and Q1. And we're basically telling Stata store the coordinates that you graph when you do this business in P1 and Q1. And so we just get the plot we saw before, basically. And we could inspect the P1 and Q1 if we want. So we can list P1, Q1, and 1 through 100. Sorry, it's an I, not 1. And we see here that for a lot of people, this is missing. But otherwise, we see these are just places on the graph. And then we do the same thing for people who are white. And then finally, while this is working in the background, I'll explain, we need to also just make a variable that's equal to 0. We'll see why we're doing that in a moment. I'm going to use the local here again to put the focus more on the new graph type and less on the long title because it is kind of long. Again, remember to run the local on the graph in the same command. And I want to, before I run this, explain what's happening here. So what we're going to do is, again, do a two-way plot. We're going to use the R area command. And what that does is tells data basically fill in the area between y coordinate 2, or the second, let's just call it the higher y coordinate, the lower y coordinate, and the run it across the x coordinate. And so what we're doing here is telling data, fill in the area between Q1, so that was the y value for the first kernel density plot, and 0, so just the x-axis, and run it across all the x values from the first kernel density, and fill it in with a translucent mode. Then do the same thing for basically the same procedure, but for the second kernel density plot up here. Give it this title, T, and remember T is going to be this local. Make the size medium. We've seen that that works best for a lot of this. Give it this Y title. And then there's a little bit here with the legend that'll make this look nice. So it's kind of complicated, but I again wanted to just show you a few things. So basically the legend says there's a few things going on here. But if we look at this, basically the position is going to put it at 2 o'clock. The column is going to put all the stuff in the legend in one column. And the ring is going to basically keep it as close as possible, since the value is 0, to the center of the graph. And finally, this is what's going to go into the legend. Okay, so let's see what this looks like, because it'll look kind of cool. It'll take a while to work here. So finally, we get the result here, and this looks pretty interesting. So it's a little bit pointy, right? But ultimately, this still kind of has this nice probability density function shape, and we can see that it, again, is kind of legible because they're translucent. And we get a lot of the same information as before, but it's maybe just on some level more aesthetically appealing to have some roundedness here. But it communicates the same basic information. So again, certainly not something you need to do on the exam, but something you may want to think about for your projects. And with that, I'll wrap up this lecture.